Yeah. So now we are ready.
Okay.
So the other one is Martin, right?
Yes,
Yes.
hello.
Uh,
Trouble connecting, but
okay.
Okay, is everyone ready?
Yeah. So fine. Go ahead.
Okay. Well, my name is Philip. As you already know, and my teammates are Jatske and Marta, but she's sick and he's here. We are interested to know more about DNA data storage with an emphasis on what problems you encounter and how you feel about it. As we
Mhm.
have told you before, the interview will only take around 15 minutes, but more is always better.
Okay.
In this interview, we will of course ask questions and hopefully learn more about the topic. Our number one priority is to keep any of your comments confidential, so do not worry. Anything will be traced back to you. If we do mention you, it will solely be your job title and work experience. In
Mhm.
addition, any comments you want to leave out, you can do so by telling us in the end of the interview. Lastly, the interview is solely by your will, so if you would like to stop at any moment, we could do so.
Mhm.
Any questions before we go forward with the interview?
So I think it's fine. I think so. Yeah, you can ask anything.
Okay.
Yeah.
Could we record this as well so we can
Yeah. Yeah. Sure.
check up
Sure.
on some things in retrospect? All right, perfect. So, my first question is, how long have you been working with DNA data storage, and what is the current state you would say DNA data storage is in? Are we near the public release or far from it? Because DNA data storage is currently very limited due to its high costs and slow read times.
So first of all, I should tell you. First of all, thank you. Both of you for asking me this question. Uh, I should say that this was around year 2012 actually. When myself, and my student, so I asked my student to whether we can do anything with DNA storage. We got this idea. At the same time, I would say that there was in year 2012 there was a first paper that came actually, which was significant in terms of DNA storage by George Church from Harvard University. So we were looking at that paper and we were thinking what to do. But before that, I was in fact in 2011 also I have asked some of the biologists about this idea. If I want to store data into DNA, what we should do actually, so
Mm-hmm.
because our expertise are in error correcting code. So whenever you want to store data anywhere, whether in your CD, DVD, hard disk, you require error correcting codes. So we thought that maybe we can develop those kind of codes if we want to store data into DNA. But but actually we were not having much idea how the things will work in the DNA storage. So at the same time, I think in 2013 we saw another paper by Nick Goldman and other people, and that paper we saw. So actually, the George Church paper, there was no error correction mechanism was there, but they have it was a significant the starting point seminal paper actually. And in 2013, the Goldman paper actually, there they have shown how they can use fourfold redundancy to correct the errors. So we thought, okay, so that means there is an opportunity for us. Maybe we can do something. So I asked one of my student, Shalin Shah, who was a BTech student, to implement that paper. And then when we did that, we realized that due to chunk architecture, which was proposed in the paper, there were issue that it was able to only encode up to 500 MB file. So we thought that how do you overcome? So we modified the chunk architecture and also we changed the encoding method there, and we were able to improve the algorithm that in that paper actually. So that was our starting point. So then we wrote that paper, that software also, the DNA cloud that we released. Using that software you can actually encode or decode any file into DNA, and
Mm-hmm.
actually, since once you get the DNA sequences for any your doc file, PDF file, or MP3 or whatever, any media file, so then those sequences you can send it to any biotech company, or you can use synthesizer. There are companies which make synthesizer, DNA synthesizer, and you can convert data into the actual physical DNA actually. So that is the thing. And remarkably, as you know that 1 gram of DNA can store 455 exabytes of data, which is in the order of 1 billion gigabytes, 10 raised to power 18. Okay,
It's a
so
lot.
it's a huge. So I mean, a couple of years back, we did this estimate that the current size of internet is around 700 exabytes. So 2 gram of DNA is sufficient to store entire internet. But obviously now this has changed. Every day we are generating a lot of data, and probably by 2025, people are saying that will be generating data in the order of 400 exabyte per day. So that is the speed at which we are generating the data. So certainly there is a challenge how to store this. How to
Mhm.
really develop the technology. So this is something. So from then, from the DNA storage. We wrote a couple of more papers, and in fact, since we had this idea that we want to use any living thing, so we also tried bacteria. So we have done an experiment at National Center for Biological Sciences, Bangalore, with our
Yeah.
collaborator, Dr. Taslim Arif. So we have actually stored a data into bacteria and retrieved it successfully. uh, you know so we did that experiment. So now, so you can actually store in bacteria. People are now trying even plants and other things. So any living organism you can try to store bacteria. Or so what we tried initially was synthetic DNA, but of course there are other living things also you can use to store data.
Yeah.
Another area that is coming up is protein data storage. So
Protein or
protein, yeah. So you can store
yeah.
data into protein, yeah, rather than DNA. So many opportunities are there right now, in terms of this thing. Now I think I should also mention that right now there is an international consortium about 30 to 40 organizations, including companies like Microsoft, Twist Biosciences, Western Digital, and Illumina. These are the co-founders, and there are a couple of
Mhm.
other organizations like IBM, Dell, and many other companies. So they have formed a consortium. We are also part of that consortium, and we are developing the standards for this technology. So how actually, because if you want to really create the technology for everyone's use, we need to develop the standards how this can be used. So that is,
Yes.
yeah. So I hope
And
soon you will see, maybe in a couple of years down the time, when you will see the real, uh, device available to you.
Harvard is also working on it, right? Or was
Pardon?
Harvard, yes, working on it or not?
Who?
Harvard University.
Yeah, Harvard University. George Church is a pioneer person actually. No, so he has done a lot of stuff, and I would say that from that paper that George Church wrote in 2012, that was a seminal paper. After that, he has written many significant papers. Recently, so basically, as I mentioned, 1 gram of DNA can store 455 exabytes of data.
Yeah.
So George Church recent paper actually last year they have shown, not last year, this year January, they have shown another interesting thing that you can actually store up to 432 exabytes. They have actually done the experiment of that. They've stored 432 exabytes of data in 1 gram of DNA. So that physical density is kind of, one can achieve. So now he has shown that, which is again a significant thing. And actually, there are two challenges actually in terms of if you want to get this technology. One is DNA sequencing, another one is, so DNA sequencing is reading the DNA, and the second thing is DNA synthesizing. So how do you synthesize the DNA? So for both of them there are machines and there are technologies. For example, there are many sequencers. Now DNA sequencing has advanced a lot because many companies are involved because of human genome projects and other activities, biotechnology area. So it has reached up to the latest one is nanopore sequencing. So which is there is a company which has created just like a pen drive kind of device which can use to read the DNA. So reading is up to that level is available now. In terms of writing DNA, there are challenges. Actually, there are three different approaches. Basically, mainly currently, what people are using is chemical DNA synthesis approach by Marvin, who was at University of Wisconsin Medicine.
Yes.
And he is actually, so that approach still people are using, but there are a lot of challenges there. There are some limitations of that approach. Recently, there is a new approach known as enzyme-based DNA synthesis that is coming up, And in fact, George Church again has done some significant work there also. You know, I think last year or this year, I don't know the exact remember the year, but I think recently he has done that also. So so Church Group at Harvard is doing a lot of stuff. Certainly.
Yeah.
You know,
Could
at
you
different
tell me more about like different problems? You said there were a lot of problems. We would like to hear more about those as well. Uh,
No, so what kind of problem you are saying in terms of doing the research or other challenges?
of like reading and writing the DNA code. You said there were a lot of problems still coming.
Yeah,
Um,
so basically, what happens? You should understand that as a coding theorist or as a communication theory scientist, you always so there is a limit how much you can store data, right? So there is something called as
yeah,
net density. So ideally, if you don't have any error correction, the ideal density will be 2 bits per nucleotide.
yeah,
But actually, once you introduce error correction, this will reduce. And so people are developing different codecs for doing encoding, decoding, and something around 1.97, 1.98, even 1.95, 1.92. Different net density codecs are available
mhm,
right now in the literature. So people are doing a lot of work there. So obviously, mm, you know, there are challenges. So that you can efficiently store data, which can
yeah,
in which you can correct it also, as many as errors are possible. So because the nature of errors are also different here. It could be insertion, deletion, or substitution of ACGT strings, when you actually store data into either in a test tube or any other place. And apart
yeah,
from that, so that is one challenge. So choosing appropriate codec so that you get the maximum density possible. But no, when we say density, I'm talking about net density as well as physical density. So as I mentioned, physical density, there is a recently yin yang codec which which was developed by George Church Group, is a very very good one actually in that sense.
hmm,
And its net density is also good, and its physical density is also very good. So we want to reach that level, the maximum density possible, and the codec should be efficient, in that sense. So this is, of course, but this is a common challenge to you know any data storage problem. You want to go to the maximum capacity that is possible in terms of how much
yes.
data you can store.
And we would like to know what are your problems that you run into while working on it. So you told us more about the problems that are in general, but what problems do you face?
So I think I mean, in terms of problem, I would say that initially when we were talking to some biologists, actually, obviously, it was difficult to convince them that yeah, this is an area which they should work, because you see, this is an interdisciplinary problem. And I'm a mathematician, so I'm always looking for, how do we basically convince a biologist to do some experiments and
Mhm.
so on. This is a challenge, obviously. But apart from that, I think another thing which I feel that many times, if you try to convince students to work into the problem, I think they think it's a biology, right? And so somebody working in computer science, for them, it's all they need to learn biology. So which is sometimes, it's a challenge, but I think slowly they understand. And I should say that, for example, I am offering this course on DNA storage and security at our university, and the registration is around 309 students, which is very large. They do like
190 students? Or
309, 309.
oh, 390.
Yeah, 309, 309.
Oh, that's a lot.
Yeah, so a lot of people are now learning about this, actually. Okay, so I think this is so people are getting motivated now. They are doing, in fact, they have done a lot of interesting projects actually in the course. So I think so it's a good thing. So initially
So
there
you're
was a bit
basically,
barrier, but now I think it's going to be a good thing. Yeah.
hmm. And well, what was the hardest, or what is the hardest problem you're facing? So is it the one you told me, that convincing biologists, or is it something else more about? technology related or
So in terms
biologically?
of
What?
technology challenge, I would say that the hardest problem is the DNA synthesis. How do we come up with a better methods in DNA synthesis which can do faster, writing of DNA actually? And I think what I feel that now the area is not new. Many people are working, and hopefully more and more people will contribute, and we will see a progress soon
And
actually.
how slow is it? Like, could you give us like a estimate of how long it takes to write it? Because
So it
apparently it's
depends on
very.
which method you are using. So normally, I think it depends on a couple of hours, or maybe depend how much data you want to write. If it is too long data, obviously it will take more time actually. So
Yes.
and one thing actually, I would say I should mention another technology challenge is, so right now main focus of everyone is about archival DNA storage. So when you want to store data for archival purpose, so you store it say for 100 years or 50 years, and then you retrieve it.
Mm-hmm.
So basically, I would say it's a cold data we are talking about, which you don't
That's not
access.
possible with DNA storage, or
No, no. So,
is it?
so this is possible. No, rewritable storage is a challenge, and there are a couple of papers in that direction as well. So, how do you look at the rewritable storage? So, the current storage that we use is basically one time, right? You just store it and then retrieve it. So basically, what we use these days in our hard disk or any pen drive or something, you can rewrite as many times as you want, right? That kind of
Mhm.
flexibility is not there in the DNA storage right now, but there are people who have done some work, and hopefully that technology also you will see. But I think currently people are mainly focusing on archival storage. Just read it once, and maybe use it occasionally, when you require it for maybe 10 years down the line or 15 years down the
Yeah.
line. Occasionally you can take the data. So that is still a challenge, and I think the way now things are progressing, I think within 8 to 9 or 10 years, we will see a lot of progress in that as well. Because now, so when we started, we thought about this issue of rewritable DNA storage, and but now I can see there are a lot of papers in that direction as well. People are actually trying to develop. Yeah.
And so in you say in 8 to 10 years, maybe we could even see like data centers being replaced by DNA storage. Is that possible, or?
Yes, I would say that that is a possibility. But as I said, for cold data, it is certainly right now very useful. When the data which you don't require quite often. But for
Yes.
if you require, and actually, if you look at, even if you say your Facebook data or any other data, right? So normally you interact, so your cold data is more as compared to your hot data. So so basically, you very small portion of data you access daily, as compared to a lot of things are for archival. So so somebody has to decide how much data you should keep it for, for archival purpose, and how much
Mm.
you want. So that kind of, somebody has to develop that kind of methods and
So
technology that.
that has also problems to like replace data centers with DNA data storage.
Yeah. So but archival purpose is, suppose that the company, any cloud storage company, they think that there is a this much portion, yeah, 60% of data or 70% of data they don't require for 10 years. They can store it in DNA storage there easily. That portion, they can obviously save cost and so on, right? I mean, in terms of, because these data centers requires a lot of space, electricity, and everything. But in the DNA storage, that is not needed actually.
Yeah. Well, last two questions. What companies do you think are ahead of the game, and what breakthroughs do they have pursuing DNA data storage?
So as I mentioned, this right now this international consortium, the DNA Storage Alliance, that is working. Now we are actually part of ISNIA Technology Affiliate. ISNIA is an international body, a non-profit organization which is controlling everything. So I think this group is going to give us direction overall, because everybody is working. So especially the Microsoft is there, Twist Biosciences, There are other companies like Catalog DNA, DNA Scrape. There are many companies in Silicon Valley which are doing a lot of work in this area actually. And IBM has also joined the hand right now. So a lot more companies. Dell is also part of it. So if you
Yeah.
look at, yeah.
Is there anything that might be useful for us finding an opportunity in DNA data storage space? We've already learned so much, but and could you state like think of potential customers or price estimate or what would be the risk of using DNA data storage with regard to security or anything else?
I think I would say that this DNA storage technology is also opening a new branch of security and cryptography. That is something now we are working on it. Actually, we have done some work actually, and already you must be knowing about JPEG DNA also, right? So JPEG DNA standard is developed by the JPEG committee right now. So that kind of work is also going on. So I think uh, security is something which people are going to think in a different way altogether, because with DNA storage and security, there are different things possible actually. Okay.
How could you like secure data on DNA data storage? How does that work?
So cryptographic techniques are there anyway, right? So for our this data also we use cryptographic techniques. Similar techniques will work there also, in the DNA storage thing also. That is not a challenge. The only thing
So
is
you
that
could
how
copy them to the DNA data
yeah,
storage
some
or
of them will, yeah. But I think as I mentioned, there are, for example, somebody has created, they have done an experiment where they took a malware, or basically a malware which is going to infect the computers. They convert it into DNA strings, send it to a company. Basically, now that company once will rewrite the DNA sequencer. They will use DNA sequencer. They rewrite the basically ACGT in terms of Excel sheet. Actually, it will. So basically, what happens? It is converted into a actual malware on the computer and infected the file. It's like DNA malware attack. That is a possibility.
yes.
Somebody has shown, right? So all kind of
Yeah.
things are possible. Mm. So
Okay. And who do you think potential customers are of DNA data storage, and who would be the first to kind of, except from the companies that are working on it, use
So I
DNA data
think
storage?
certainly, as I mentioned, that even there could be many governments or any organization which is having data which is actually cold data, which they don't use often. They will be the first
Mhm.
customers to basically restore data. So
So
basically,
they would switch from, because Amazon Glacier, or how do you call it, also uses data to store that is not being used. Would they replace it for DNA data storage?
yeah, I'm not
Or
sure about what Amazon is doing right now, but I'm saying that in terms of potential, any organization which has a lot of cold data and which they don't use often, they can certainly use the
yes.
technology. Yeah. So
Okay. And what would be the price estimate if you would guess? Would it
well,
be very expensive or?
I think that will take some time, probably another 4 or 5 years, because see, now people are working to reduce the cost. Actually, obviously it is. I would say that if it is something around, uh, say, $100 per terabyte, if we can reach up to that level, then probably people are going to use it, right? Or still that will
Yes.
be a little bit costly, but I think it will slowly come down actually, because
Yeah.
people are looking on how to reduce the, because then there will be more competitors in the area, more and more companies will work, and certainly there will be a price competition, right? Who can do it at
Yeah.
a lower price? Yeah. So from business as prospect also, there are so many things possible.
Yeah. Thank you. Well, that's it for our questions. I really appreciate you having us, and we learned so much from you. Um, well, thanks again, and
Thank you very much. It was nice talking to you. So I think I will be putting it on online, right, so that more people can benefit out of it, right?
yes, yes, that's
Okay.
perfectly fine.
Thank you very much.
Thank you
Thank
very
you, and
much for
have a
your
nice
time.
day.
Yeah.
Thank you.